All right, let's get started. So I know I'm really excited. I know Ryan is very excited. I know Sarah's very excited, and I hope everyone else is very excited too. Today we've got Sara Delano Moore. She is currently the Vice President of Content and Research at Origo Education. She is also an educational consultant. She's been a classroom teacher. She's been a teacher educator. She is co-author of a couple of series of books, one Mastering Math Manipulatives, and the other one is Mathematize It. And knowing Sara, I know that this is going to be just a wonderful, wonderful webinar, very informative on how you can incorporate math manipulatives effectively into your classroom. So it gives me really great pleasure to turn it over to Sara Moore. Sara, I'm going to sit back, I'm going to listen, I'm going to learn, and I'm looking forward to everyone's aha moments today.
Well, thanks, Mark. It's great to be here, and I so appreciate you and Ryan and the Braining Camp team inviting me to do this. You and I have worked together for a long time, off and on, and teaching with manipulatives matters. I'll start there, and we can begin to think together about this. Let me adjust my screen so I can still see the chat, because that's important. You all don't want to see the chat. There we go. The joys of technology. All right, let's talk about manipulatives and really how do we use them well when we're teaching kids. I love manipulatives. I've always taught with them. And yet, when I work with teachers, I spent part of my career working with pre-service teachers. I've done a lot of coaching and professional learning in different forms. I always get some basic questions. It's all this stuff. How do I manage it? Do I want physical tools? Do I want digital tools? You know, I came of age in a time when digital tools weren't an option. My Cuisinart rod set that my mother got me in elementary school is still in the basement and still would be my desert island manipulative. So why I'm not using them today, I'm not sure, but it is. But do I use physical? Do I use digital? How do I weave them into lessons? Okay, we have this great time building stuff and working with the manipulatives, either physically or on the screen, but then the test doesn't let them use manipulatives. So now what do I do? All of these questions come up. And while we can't save the world today, we can begin to talk about some of these big ideas. And as we do that, I'm going to share a few key things in slides, and then I've got 4 math examples that we'll do in Braining Camp. So if you've got your codes in and accounts set up, Mark and Ryan will put the magic codes for the activities I'm going to model in the chat as we get to those things. Here they come, perfect. And you'll be able to do the math with me. So why manipulatives? Kim and I, as Mark said, have written and thought a lot about this question and are passionate about it. Manipulatives matter because everything we do in math is one of 5 representations. So over on the left of this graphic at 9 o'clock, you see concrete. Concrete tools are physical manipulatives. The counters that we choose and all of those kinds of things. Moving to the right, clockwise, up at noon is visuals. Draw a picture. Nobody's banned scratch paper, whether on a print test or a digital test. As far as I'm aware, nobody's banned scratch paper. So if kids can draw a picture of the manipulatives, and we'll model some of that together today, they can carry that thinking with them. Ultimately, on the right at 3 o'clock is symbolic mathematics, book math, equations and number sentences and all of those kinds of things. And this arc across the top of this graphic is what people often talk about as CRA, concrete representational abstract, or CPA, concrete pictorial abstract. It's a very Piagetian approach to teaching math. Down on the bottom are the other two representations that we don't talk about as much, but they matter. At the bottom right, verbal is the language of mathematics. For instance, how do we read a decimal? Do we read it 1.35, 1.35, 1 35 hundredths? How do I read x with an exponent of 2? X2, x squared? That how do I say it is critically important, whether I'm talking about the manipulatives I'm using or the equations and symbols. And then last but not least, at bottom left is the idea of context. Word problems in their simplest form in school, but also the mathematical modeling that happens as we use math in our lives. Where is the mathematics in setting the table and knowing how many knives and forks and spoons and plates do I need to get out if I'm going to do that? There's math in that. And so when we think about teaching with manipulatives and why we use them, it's because if we only teach math from a symbolic perspective, if all we do is the book and squiggles on the page, then only some kids get access to the math. On the other hand, if we allow manipulatives as physical or virtual tools, pictures, visuals, they can be informal sketches, or a chart, a graph, a diagram counts as a visual too. We start talking about mathematics in context, not just naked numbers. And we tell kids the language of talking with mathematics. If we do those things, now we've given everybody access to the math. And that's why manipulatives matter. As we think more specifically about what manipulatives do, they provide a visual or a physical image, depending on whether we're virtual or physical, for the math. They provide us ways of representing math both proportionately and non-proportionately. They provide an access point for students who may not be confident of the language. I see Saguna's question about writing in math. To me, that's largely the verbal. It's simply in a print form. But that's an interesting question. I never thought specifically about writing. So let's play with that idea as we go. Manipulatives in any form do these things on the left. On the right, if I have physical tools, kids can hold them in their hands. It's easier to say, take 10 minutes and go play. They're relationships that you can see sometimes better in 3D. I find when I work with virtual manipulatives, or when I first started to work with virtual manipulatives, I had a much easier time navigating the tools that I had used physically because I kind of knew what they could do and I knew what to expect. That may be because I'm old and the technology world is newer to me, but it may also be true for some students. On the virtual side, the first thing I came to love about virtual manipulatives when I first began working with them is there's an endless supply of pieces. If you're working with a set of fraction towers or fraction bars, you've got 4 1/4 pieces. But if you want to help children count by unit fractions, it's nice to have more than that. 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4. And with that endless supply, I have that. Often there are work mats built in. You can annotate and screenshot things. Braining Camp gives us this lovely ability to set a code and share it. You'll see me using that in just a moment, so that I can, as the teacher, prepare an activity and then have my students all start in the same place. Because when they're on a screen, it's harder to know, is everybody set and ready to go for the experience we have coming? If it's physical manipulatives on the table, I can skim the room and tell. But when it's virtual, that's harder. So the code allows us to do that. So let's do some math, because that's why we're here. I'm going to switch over to Braining Camp Live and do 2 examples. The first is multiplying two two-digit numbers, which will let us think about proportional and non-proportional models and help kids move from the manipulatives to the algorithm. And then we'll solve a very simple subtraction word problem, the kind of thing a first grader might look at, and talk a little more about physical and digital manipulatives. So let me and go back to here, because that's the first one. So Mark just popped the code in for this. If you enter that on your screen, you should end up with the same thing I'm showing. And I've got virtual base 10 blocks set up here to multiply 12 by 13. When I learned to multiply, it was procedural display. The teacher said, do this, do this. There were some lies, misstatements, untruths. I don't think my teacher was intentionally lying to me, but mathematically, some of what we say isn't true. And I did well in math because I could memorize. And there were other kids in class who didn't memorize well and couldn't kind of keep track of what was going on. I got sent to the principal's office once for asking why. I don't know if it was about this topic. I don't remember that part, but you need to understand. So right now I have the base 10 blocks set up by color so that you can see each piece is a different color. Very often when you're introducing this tool to students, this is a great way to think about it, because like with pattern blocks, grab the unit, that's the yellow. Grab the flat, that's the orange. Grab the hexagon, that's yellow. I'm going to switch them to single colors because I want us to focus on some different things today. So I'm going to have them all blue. And I'm first using an area model. This is a proportional model in the sense that this rod that represents the 10 part of 12 is 10 times as big as the unit. And so the first thing I'm going to think about is, how do I fill in this area? Well, 10 times 10, that's 100. That's easy. 10 times 3 is 10, 20, 30. And then 2, I'm going to think about this as 2 times 13. So let's see. Oh, I know Ryan showed me the magic trick to select. There it is. Oh, I copied the wrong thing. Sorry. I'm going to go ahead and drag them in here and turn them. And Ryan can correct me later about how to do it. But I'll rotate. And then I can make a copy and put another one down there. And let's see if I can grab that collection. We'll just bring one down. This is why we always practice first. But so I'm going to end up filling in my 6 here. And the other thing I'll tell you that I do with students sometimes who get frustrated with this part, whether with objects or numbers, is I'll just write a 6. Just, it's 6. If you know your fact, just fill it in. If you don't, it's okay. So I can count what's on the inside here and say 100, 10, 20, 30, 40, 50, 56. My 152 is what I've dragged in. I didn't drag all 6. So think about that with your students. But my answer then becomes 12 times 13 is 156. So now that's great. But only people with jobs like ours wander around in life hauling suitcases full of base 10 blocks or links to virtual base 10 blocks to make this happen. We need to teach kids how to make those translations across representations. So hiding here, I've got an open array. You can see, I hope, the resemblance between this and the base 10 block model I just built. Jill, I see your question. I'll answer it in just a moment. And I can think here, 10 add 3, there's my 10 add 3 on the left, 10 add 2 vertically, 10 times 10, that's 100. 10 times 3, that's 30. 10 times 2, that's 20. 2 times 3, that's 6. Add them all up, 156. This model's non-proportional. My 4 boxes are the same size, even though one contains a value of 6 and one contains a value of 100, and the other 2 are in the middle. That's okay, but developmentally, kids need to make that move from the proportional model of base 10 blocks to understand how much bigger 100 is than 10 or than 1, to this non-proportional model that's more efficient. Ultimately, again, we want to get to more symbolic math. I would call this open array that I just sketched on a visual representation. It's got some symbols in it. Ultimately, what I want to get to is this. This is a model called partial products. And if you look at it, this is where I laugh and say, I know it wasn't intentional, but my teachers lied. 2 times 3 really is 6, but that was never 2 times 1. It's 2 times 10. So 2 times 10 is 20. 10 times 3 is 30. 10 times 10, that's 100. Add them all up, it's 156. This counts as a standard algorithm. The more traditional form is a little more compact, but I find this way is easier for students to think about and build that bridge so I can see 10 times 10 all the way across. I can see it in the flat on the left. I can see it in my open array at the top left here, and I can see it in my partial products model over here. If students see all of those, this is how they carry that thinking through in their work. And I may not have base 10 blocks, but I can draw a picture. I can also draw a picture. Let me grab a different color pen here to come back to the question about how would you create this model if we weren't working in teen numbers. Jill, your example of 47 and 23, I'm going to sketch it. 10, 20, 1, 2, 3, 10, 20, 30, 40, 1, 2, 3, 4, 5, 6, 7. I apologies for running off the screen, but I would build that, or this is how I might freehand sketch the base 10 blocks. On that note, for my students, I taught 6th grade for much of my classroom career, and my students would draw the flat and think that they needed to put all the lines in it to get 100 squares in an hour and 8 pieces of paper erased through. Later, we still hadn't done it. So our convention was that we just wrote the number 100 in there. Use that if it's helpful to you. I can use this approach with any 2 factors. If I have more, if I have a 3-digit number, I would simply work with, I'm going to erase all of this to give myself some room. I would say 100 plus 20 plus 4 times 30 plus 6. 100 times 30 is 3,000. 20 times 30 is 600, and continue filling them in. That's not practical with the blocks, either physically or virtually, because wonky stuff goes on. But this approach and then the partial products approach on the right work great no matter how big the numbers are. It's a terrific way of thinking about it. So that gives you a sense of this idea of connecting representations and the move from proportional to non-proportional models as we go for this first example. In our second example, I'm doing a simple first grade word problem. So Mark's just popped the code for this. Again, if you pop it in on your screen, you'll see my lovely drawing of 5 frogs on a log. This is where I did take advantage of the fact that I can change the color of my 2 color counters. I don't know about you, but my kindergarten headed into first grade granddaughter would not accept a yellow or a red frog. Frogs are green. So I love the fact that we can make them green. I chose to use the pen to draw my log. I could also come over here if I wanted to and grab a rectangle and color it brown, and I've got a different kind of log. Use the tools that work for you. I like to model sketching with young ones because I want them to think about what would I do with actual physical counters and a piece of paper in front of me. I would take my crayon or my marker and I'd draw a log. And I would take my 5 counters, whether they were actual little toy frogs or just discs like this, and use them. So let's think about problem solving now in the sense of act it out. This is where we're connecting context, the story problem, to what we do with the manipulatives. And I've deliberately typed each step of the problem on a line so that it's easier for us to see. There were 5 frogs on the log, and I've built a model for that. I've drawn my log. I've got 5 counters on there representing my 5 frogs. Some of the frogs hopped off the log. That's great. That means some of them left, but I don't know how many. At the end, there were 3 frogs left on the log. So if you look at what I just did, too many frogs hopped off because I've got 2 frogs on my log. So put you back. You're not ready to go play yet. How many frogs hopped off the log? 2. I acted out the story. In this case, it's a change unknown situation. I know the beginning and the end, and I'm trying to figure out what's happening in the middle. But I would use the same approach if the problem said 5 frogs, 3 hopped off, how many were left? Or 2 hopped off, how many were left? And I can craft a number sentence here. There were 5 frogs on the log. Some of them hopped off. Hopped off or leaving mathematically typically means we're subtracting. But we don't know how many hopped off. So we're just going to leave that blank. And at the end of the story, there were 3 frogs left. And so I can use the pen in terms of virtual manipulatives. This is a great example of I can annotate. I can make connections here. I can color code things if I want to. I'm helping students see, act it out, all sorts of things. If you're working in with a part whole context, there is a workspace mat for that. I like to draw the pictures for these action ones and use that part whole workspace context for comparisons and part whole problems where there is no action. The notion of children on the playground, boys, girls, children, or teachers, students, people, those different ideas. But you have lots of different workspaces you can use in order to create this. I used the factor track workspace with the base 10 blocks. I drew my own here because I wanted it to connect to the context of my problem. But this is 2 examples of how we use this. Let me jump back to PowerPoint for just a moment. And let's talk about physical manipulatives and managing them. Because it's a lot of stuff. And so you've got to think about what does that mean in your classroom? Anytime you're introducing a physical manipulative, start with that free exploration. If you're teaching kindergarten, that might simply be have it in a center or a station where kids can work creatively with it. Gradually form, it might be in a in my 6th grade class, if we were using a new tool, I'd set my timer for 3 minutes or 5 minutes, depending on what the manipulative was. It's obviously can be shorter for 2-color counters than Cuisinart rods or fraction tools. And say, you've got till the bell rings. Be responsible humans. We'll talk about that with ground rules in a moment. And then to bring the conversation towards the math, use a notice and wonder routine. What do you notice about these pieces? What do you wonder about them? I notice with Cuisinart rods that the unit can be strung together to make all the other rods. Those kinds of things. Make it easy for kids to access manipulatives. This one's critically important for 2 reasons. Number one, these tools are an extension of kids' brains and hands. This is another way to think about and be successful with math. It's an access question. It's an equity question. So everybody needs to be able to get to it. Depending on your classroom, that might mean devices available and some guidance about when you can open up and log in and how to handle that appropriately. If it's physical manipulatives, I used to keep table sets of manipulatives in baskets in the middle of the table. My friend Kim, who co-authored the books with me, she's more of a primary grades person. She said, and what I did with that in kindergarten, 1st grade, is I added to the basket as we learned about new manipulatives. The first manipulative we learned about was linking cubes. So initially, that's all that's in the basket. And then as we learn about 2-color counters, we'll add those to the basket. And as we learn about this other tool, we'll add that to the basket, maybe pattern blocks. So with older students, you might start with more options at once, depending on what their background is. But you can keep it moving with that idea so that nobody has to get up to get them. Because as soon as I have to get up to get my manipulatives, I call attention to the fact that I need them, and it ought to be normal. If you have a classroom where there's a lot of kids getting up and walking around to get all kinds of things, then have them in baskets on the bookshelves, and kids are welcome to get up and get them as they want. But think about what you're asking students to do in terms of the position we put them in with access. Make it, excuse me, make it easy, make it unobtrusive, so that kids know this is just the way we do this. This is just part of what happens. And then we need some ground rules. Part of that fundamentally is these are tools, not toys. So let's talk about how we use tools. When we use a hammer, when we use a protractor, all different kinds of tools. What do we do with tools? Tools have specific purposes. They can be used creatively. So it's not that you can only use a hammer to put a nail in a wall, but think about how you're using a hammer. And if you need to break a piece of glass, yes, that might do it. But look at what we do there. My basic ground rule, well, I had 2 rules in my classroom. You're responsible for your own learning and don't interfere with anybody else's learning. The way don't interfere with anybody else's learning translated to my 6th graders was the manipulatives have to be in contact with your hand or the desk. That covered most things. With geoboards and geobands, I have a dear friend who taught kindergarten and 1st grade for 30 years, and she said, you just tell them that geobands can't fly. And if they have something that's flying, they must have the wrong equipment. And I'm ever so sorry, but we'll have to take it back and try again. And you say that to a kindergartner and they believe it. You say it to a 6th grader, they think you believe it. And so they're scared. You've got to have some basic how do we behave rules. And most of us with geoboards can tell the difference between the band slipped off my finger and I went, I'm going to get you. So we've got to think about that. Mark and Ryan have posted some links to some of the tutorials and some ideas for exploring the virtual manips. And I see Arlita's comment about individual desks in the center of the table. The other thing I see is the backpack for the chair. Yep. The zip tie a pencil pouch. That's a great idea. Or in primary classrooms, kids often have a little sleeve that hooks over the back of their chair and holds things. It's kind of like a backpack for the chair. You could put the manipulatives there. And make them available. But the point is to think about, as you are, how can we make things available? Sometimes you put your desks in groups of 4, you get a table. Sometimes they have that funky angle and they don't sit nicely, and it just depends on your furniture. But think about using a basket, think about tying a pencil pouch, all sorts of options. The point is, make them accessible. So let's do a little more math, because we've got 2 more examples, and we're going to move. The main purpose of these 2 examples is to use manipulatives to help children understand that it's still what you learned with whole numbers. Because when they get to fractions, when they get to integers, very often what children think is, this is a whole new form of math. Or this is a whole different thing that we just teach in math class. Fractions are this exotic venture that gets taught during math time. And it's still just a number. It lets us do some different things. So we're going to subtract a negative. Again, always this idea of connecting representations and reinforcing that it's still the subtraction you know and love from kinder and first grade. And then we're going to talk a little bit about dividing a fraction by a fraction, because that, by the way, is still division. So Mark has put the code in, and subtracting a negative. So what I've done here, I'm using algebra tiles in this case. You can use 2-color counters, lots of options. For subtract 2, that we learned in primary grades, K and 1, is actually +4 take away +2. But we don't talk about the positive part. And I think we don't for 2 reasons. One, it's our convention. We very rarely say +2 or +4. And little kids don't know there's a negative. They haven't learned that part yet. I'm a huge fan of number lines that have the arrow going to the left of the 0 so that kids realize something's there. But that's a soapbox on the side. So just like my frogs on the log example, +4, I have these 4 counters here. Remove 2 of them. So in this case, I'm taking them away. I'm dragging them. And then what's left? What's left is actually +2. And yes, David, kids in Canada learn about negative numbers very quickly thanks to the thermometer. Kids in countries that are metric learn negative numbers from the thermometer even more quickly. I'm in Northeast Ohio. We don't get there too often on the Fahrenheit scale, but any context we can take, we'll take it. So now what I've got to think about is that for subtract -2, let's uncover this part, is exactly the same problem, except what I'm taking away is not a +2, but a -2. And I don't have any -2s in my model. I've still just got the 4 I started with, the +4 I started with. But use your math. What can I add to any problem and not change the quantity? It's that identity property for addition, if we want to get formal about it. It is the magic of adding 0. Zero pairs, exactly. Danielle knows where I'm going. So let's uncover this. I'm going to add some zero pairs. So let's see. There we go. So this, I'll erase this plus zero. This still says, there. This still says 4 on the mat, right? But now I can remove, because frogs hopping off the log, that's what subtraction is, -2. Whoops. Come on. There we go. There's 1 gone. Here's another one gone. This guy, it's my tablet, it's not Braden Camp. This guy is still a 0. 4 subtract -2. The net effect here is, do it on this screen. +6. Because that one is still a 0. So what I'm showing students here is that subtraction is still subtraction. I did, Marion, put too many 0 pairs on, and that, whether it's too many, as you ask, is an interesting question. Where I go with this in my own teaching is to have children start with a bank of 5 0 pairs. I only had 3 on the screen here. So my 0 mat has 5 0 pairs. And early on, every example I give kids, what you're subtracting is 5 or fewer. And then we clean up the extras. I know that sometimes we teach children, since you want to take away -2, you're going to put 2 0 pairs on. In some ways, I think that's as confusing as having to deal with the extra. It's just differently confusing. I would encourage you to play with both approaches and think about what works best. It may be that different approaches work better for different students. My students generally notice I didn't need that many, and they begin to imagine what they need to do without actually having the counters. And that raises a really important point. We've got to think about, how do we help students kind of fade the use of the manipulatives? Naturally, one of the ways to do that is to increase the quantities in the problem so that the manipulatives become less efficient. Just like tally marks, eventually they become inefficient. And so we need to learn a new way. But what we're thinking about here is, I'm still just taking away like I always did, but now I've got 2 different things I could take away. I have a +1, I have a -1. So which is it? That's what negative numbers add to the mix. It doesn't change subtraction. And when we look at it this way, whether we put in exactly the number of 0 pairs or just start with that open bank, we help children see that subtraction is still subtraction. And yes, I can begin to figure out, 4 subtract -2 is the same as 4 add +2. And they understand where it comes from. It's not a mathematical magic trick, where keep, change is a mathematical magic trick. Gets me to the same result, but not as happily. Let's look at our last example, where we're going to divide a fraction by a fraction. This is another moment where we are thinking about what we do. I see that number line question. Let me talk about fractions first, and then if we have time in Q&A, I'll come back to that number line idea, because it's a great question. Fractions, yep, Mark's got the code up. Fraction division. Again, it's still division. So I'm going to begin with 4 divided by 2. And if I'm working with naked numbers, just abstract computation, symbols, what that means, one of the ways I can think about that is how many groups of 2 are in 4? And there are 2 of them. I can see that in what I'm doing. So if I look at a fraction division problem, that underlying question, how many of these are in those? It's that repeated subtraction idea is what we need here. So let's get rid of this. 1/2 divided by 1/4. How many 1/4ths, I'm sorry, are in 1/2? Well, I've already put one of them on there. And if I want to match it up, here's my second one. How many 1/4ths are in 1/2? There are 2. Ultimately, do I want kids to think about how they can model this without reasoning about it? Teach them things like invert and multiply or divide across, whichever your approach is? Yes. But initially, when I first talk about fraction division, I need to build kids' number sense with fractions. Because intuitively, children think, based on whole number work, division makes things small. There is nothing small about 1/2 divided by 1/4 equals 2. You have to be able to reason about it. So how many 1/4 cup measuring cups does it take to fill a 1/2 cup or to empty the 1/2 cup, if you want to give it that context? How many of these fraction tiles, fraction bars, fraction circles, choose your favorites, are there? The logic is how many of these in those, and estimate. 1, less than 1, more than 1? What's going on? Spend some time in that space so that kids build their intuitive sense of what's going on with fractions. And you can do this, 1/2 divided by 1/2. How many 1/2s are in 1/2? Well, there are 3. And isn't it interesting that another name for 1/2 is 3/2? While I know we were all exasperated by the fact that the Common Core didn't include simplest form in the standards, I think it's a real gift. Because I can see things by thinking about 3/2 divided by 1/2. I have 3 1/2 pieces. How many 1/2 pieces is that? How many 1/2s are in 3 1/2 pieces? 3. I can see that in a way I can't with 1/2. It's just how it works. So this one's fairly straightforward. And then, of course, we get to the really interesting one. Where? There we go. 1/2 divided by 1/3. So how many 1/3s are in 1/2? Exactly 1, less than 1, more than 1, a lot more than 1. Do that estimating first. Well, there's at least 1, but there's not a second one. Because if I put a second one on the train, yeah, less than 2, it goes out too far. So this is the trick about fraction divisions and remainders. It's 1 and a bit. And now the whole for the fraction changes, because there's 1 whole 1/3 and there's half of. I would have kids exploring this, but I'm going to cheat because you all are grown-ups. There's half of the other 1/3. So there are 1.5 1/3s in 1/2. This is where the verbal part. How do I write it? How do I say it? There are 1.5 1/3s in 1/2. I typically, Ryan's right. We can turn the labels off. Let me. There, gone. It's up to you. And turning them off at this point where we're figuring that one half can be nice if you've got the physical tool, rotate it or flip it to a blank side so that kids can see that. I will typically, once kids have a good intuitive sense of this, show them two ways of doing things. I'll show them divide across, numerator divided by numerator, denominator divided by denominator, and I'll show them invert and multiply. And we'll test it a few times. In fact, in the 4-8 manipulative book, there's a whole activity that shows why invert and multiply works, what's happening when you invert and multiply. Whether I want to use this example, 1/2 divided by 1/3, is not friendly for divide across because you end up with 2/3 in the denominator and no. But for other problems, divide across is great. So if students have both strategies, then they can think about both pieces, both methods, and decide what makes sense to me. Fundamentally, Judy, you've got it exactly. The focus is on the math. And manipulatives allow us to focus on the math in a way that's not theoretical, that kids can see and build and hang on to and touch. What do I mean by divide across? Let's see. 3/10. I'm going to choose friendly numbers here. Divided by 1/5. Divide across means so there are 1.5 1/5 in 3/10. So let's look at that. Oh, I need my labels back on. And I grabbed a 12th. That was not what I wanted. Make that go away. I've forgotten the colors. 3/10, 1/5. Yeah, visually it makes sense that there's 1.5 1/5 in 3/10. So that's what divide across is. And obviously then I can also do the invert and multiply thing. And I'll end up with 15/10, which is another form of 1.5. But in both cases, it's about do the math. Let me switch back to PowerPoint because we're close on time. And a couple of closing thoughts here, and I hope Mark and Ryan will come up if there are questions I've missed or other observations. One of the takeaways I hope you have here is that manipulatives are an exploratory tool. We talk a lot in the Mathematize It books about having kids play in a mathematical sandbox, and manips are how we do that. One of the ways we do that. Make them available to students, whether digitally or physically. Give them some choice about what to use and when. I think it's reasonable to say, you've got to use base 10 blocks right now because I want to make sure you know this skill and strategy, how to use this manipulative for this structure. But at other times when students are working more open-endedly, they may decide they want to use pattern blocks for fractions. Go for it. We don't have to monitor their tools in that way. Remember, we've got that practice of use appropriate tools strategically. Even if they make a bad choice, they figure that out. That's part of becoming strategic. And then show students, as I've modeled here, how to connect their manipulative work to other mathematical representations, because that's where deep learning happens. That's where this goes.